So let's get started. So good day guys, welcome to Math 1700 tutorials. My name is YG, I am the lab instructor. In our tutorials, we will be basically working on the worksheets on the UMLearn. And the questions on the worksheets are actually very similar to the questions in our lecture notes. So what we are doing here is basically reinforcing our technique of solving the problems, as well as getting ourselves more familiar with the materials. So now let's get started to work on the first question. So for the first question, for the following expressions, simplify the expression if it is well defined or explain why it is not defined. So let me copy and paste them. Here. Okay. So for the first one, question A here, we have sine inverse of pi over 4. The steps of working out this is always use the definition. Right? So we will let theta equal to this inverse function of pi over 4, right? And by our definition, we will have sine theta it is equal to pi over 4, where theta is an angle selected from this interval from negative pi over 2 to pi over 2. Right? Of course, we need to justify why this expression is defined. I mean this expression. Because for the inverse function, the domain is from negative 1 to 1, right? And this, this pi over 4 is inside this interval. We know that pi is approximately 3.14 something. So pi divided by 4 is less than 1. And it's positive, so we need to give this justification, of course, but this is kind of obvious, and that is why this expression is defined. And after knowing that, we use this expression to substitute back to our original expression. This is sine of this guy here, this inverse, right? And we have denoted that this by theta. So this expression here is actually sine theta. What is sine theta? Well, sine theta by definition is pi over 4. So this answer is just pi over 4. Very simple. And more generally speaking, whenever we have an expression like sine inverse of x, this x is an abstract symbol, maybe 2 pi, maybe pi, maybe some whatever values. Right? This thing is always equal to x as long as this x is inside our domain from negative 1 to 1. It's sort of like this function and this inverse function cancel out. So that is the summary of this question. Whenever you see this thing, make sure that the value x is inside the domain of the inverse function. Then you can just cross out this, and the answer is just x. Okay, so that is our question A. What I do want to emphasize here is that the question A is different from question B if you look at them closely. Why is that? Because the question A here, you see the inverse function is inside, right? And this inverse function here for the second question is kind of outside. So for the one inside, you will see that it's relatively easier. And for the second one, you need to put in a little bit more work. So let's try to work on the second one here. For the second one, same step. Whenever you see a inverse function, you will let this inverse this thing equal to theta, right? And by our definition, cos theta is equal to cos 27 pi over 5. And theta is the unique angle selected from this interval from 0 to pi, according to the definition of the inverse of the cosine function. Of course, before doing that, we need to give a justification that this expression is well defined, and that is because the thing that being evaluated by the inverse cosine function, this one is always between -1 and 1. That's the bounds of the trig function, cosine function. So we say easier justification. Now compare this to the first question. We need a little bit more work here to work out this theta. Theta is not just this 27 pi over 5, right? Because we require that this theta be in this interval. So what do we do here? What do we do for this 27 pi over 5? Is that we want to decompose this angle into the sum of a multiple of even multiple of 2 pi plus a small angle, so that that angle is inside our domain, inside the interval, I should say, from 0 to pi. And there are many ways of decomposing this. It's not unique. You need to try out your ways, right? So for example, I can rewrite this 27 pi over 5 as 20 over 5 pi plus the 7 over 5 pi, which is 4 pi plus 7 over 5 pi. And this 4 pi is even multiple of 2 pi, so we can just ignore it. When these two things evaluated by cosine, they are the same because 2 pi is a period, right? But notice that if we decompose it this way, this angle is still way too large for us. It's not inside this interval, right? So you may want to try another way to reduce it. For example, I can write this 27 pi over 5 as 30 pi over 5 minus 3 over 5 pi, which is 6 pi minus 3 5 over pi, right? And 6 pi here is a multiple of 2 pi, right? So we can just ignore it. It's still a period. But for our angle here, it becomes negative, right? You may say that it's still not in our interval, but we have some trick to turn this sign into positive, right? Because now at least that this angle is small enough, so when evaluated on both sides, by cos. We have that. This is cos negative 3 over 5 pi. And we know that cos function is an even function. Even function has the ability to swallow this negative sign. So this immediately turns into cos 3 pi over 5. Right? So now we have found the angle 3 pi over 5, this one, which is inside our interval that is required, and it has the same cosine value as the angle 27 pi over 5, right? So this 3 pi over 5 is the perfect candidate for our theta, and actually the unique candidate. So we have that theta is equal to 3 pi over 5. Right? This is the answer. And if you compare this with the first question, you see that the second question actually requires a little bit more work. Okay, so that is question 1. Now let's work on question 2. Not at question 2, question 1, but question C and question D. So I may not be able to go over all the questions because we only have 50 minutes, but I will go over the main questions. So for this question here, firstly, we see that this -1 evaluated at the inverse function of cosine is equal to pi. If you're not familiar with the value here, why this is pi, I draw this unit circle for you to kind of get you familiar with this trig value, this trig function value. So this is 0, right? And this angle here is approximately 6 pi over 6. If you cut this quarter in half, this is pi over 4. And this one here is pi over 3. The y-axis here is corresponding to pi over 2. Well, this is 2 pi over 3. And this angle here is, 3 pi over 4. This is 5 pi over 6. This is pi. So when we're looking at the cos value, we're talking about the x-coordinate. When the x-coordinate is -1, you see that this point is here, and this is corresponding to the pi, theta equal to pi. Right? So this one here is pi. So what we are looking at here is actually sine -1, or sine inverse of pi. We know that by our definition, the domain of the inverse of the sine function is from -1 to 1, right? So you see that this pi is not inside this domain, which means that this is not defined because pi is 3.14 something. Right? So that is question C, not defined. Now let's work on our question D. This question is very complicated. So let's go slowly, step by step. We work on the most inside one first. What is cosecant? Cosecant is 1 over sine something, right? So we work this out. This 1 over 2 SEC here, a CSC actually, is equal to 1 over 2, 1 over sine of 2 pi over 3. Right. And you look at the value table, this is 1 over 2 times 1 over square root of 3 over 2. So that is equal to this 2 cancel with this 2, right? So this is equal to 1 over square root of 3. And after working this out, the second step, we're looking at cos -1, not cos, like cotangent -1 of, that's 1 over. Right. Now let this equal to theta. So we have our cotangent theta equal to 1 over square root of 3, where theta is from our negative pi over 2 to 0, union 0 from pi over 2. Now we can select this angle from here by looking at the unit circle. This is obviously pi over 3. Because when theta is equal to pi over 3, tangent theta is square root of 3, which implies that the cotangent is 1 over square root of 3. And for this interval here, the value is negative. Right? So we have our theta here. Right? And the third step, plug this in back into the sine. So the sine of this thing is sine theta is equal to sine pi over 3, right? Which is square root of 3 over 2. So that is our final answer, square root of 3 over 2. A little bit complicated, but you see that the steps are exactly the same. As long as you follow the steps correctly, it's just a little bit lengthy. It's long, but it's not very difficult. Okay? So that is our question 2. So maybe let's work on the second question. I will leave the rest of the 4 questions for you guys to solve. They are similar to the first 4 questions. So I will solve this in case that I am running out of time. So use implicit differentiation to derive the formula for the derivative of the cotangent. So for a question like this, you need to write out the expression y equal to cotangent inverse of x first, right? This is a function of x, right? And by our definition, we rewrite this so that we get rid of the inverse function. All we have is x equal to cotangent of y, right? And now we differentiate both sides with respect to x. So on the left side, is equal to 1. That is d over dx, right? D over dx of this x, right, equal to d over dx, this cotangent of y. Right? So the left side is equal to 1. While the right side, you need to apply the chain rule. I remind you here, if you're not familiar with the chain rule, you need to review the 1500 stuff. So that is the chain rule here. The chain rule here, you have 2 layers. For the first layer, that is the cotangent function. We know that the derivative for the cotangent function is negative cosecant CSC square of y. And for the second layer, that is the derivative of the inside function with respect to x. So that is dy over dx. Excuse me. Now, after applying the chain rule, we want to solve for dy over dx. Right? So we solve it, dy over dx. It's equal to negative of 1 over CSC square y. That is the derivative. But this derivative is not written in the desired form that we want, because we want it to be written in terms of x, not in terms of y. So that is why it needs a little bit more work to turn this or to rewrite this in terms of x. How do we do that? So this is CSC, right? CSC is 1 over sine. So it's negative of 1 over, this is 1 over sine square of y. So it becomes negative of sine square of y. And for this, we can view this as sine square of y over 1, because it doesn't hurt me to put 1 in our denominator. Anything divided by 1 is equal to itself. Right? But the reason I put this 1 here is because we want to use the identity that cos square y plus sine square y is equal to 1. We want to use it to replace this 1 with this cos square y plus sine square y. Okay. And after that, we divide the top and the bottom by sine square. So this divided by the sine square y. The bottom also divided by sine square of y. So we have now negative 1 over this cotangent square of y plus 1. Right? Keep in mind, what is our cotangent? The cotangent is here. Right? This is our cotangent. Right? And now we substitute. This becomes negative x squared plus 1, which is our derivative. You may think that this seems very mysterious, but actually it's not. If you don't want to go over these steps, you can just memorize the another identity derived from this identity. That is, you can just memorize that CSC square theta is equal to 1 plus cotangent square theta. Right. but most of the time we may find it difficult to memorize this. If you don't want to memorize this, you can just remember to use this identity to go over these steps to work this out. It's not very difficult. So it's that you either memorize this formula or you use this one to derive the answer. But either of these steps should be straightforward. So that is our question 2. Okay. Now let's move on to the question 3 here. Question 3 it seems a little bit intimidating. Differentiate the following functions and simplify the answer as much as possible. We know that in our 1500 we don't have to simplify the the expression, right? But here asks us to simplify, so you may need to be careful about your computation, right? So it's more difficult here. Simplify this answer. And the reason that we want you to simplify is because we want you to kind of understand how those inverse function and the original function are working together. We want you to understand the rules. So here, for this question, you know that the a is a constant, right? Constant number, right? So dy over dx, you factor out this constant, right? And it becomes the derivative of the tangent inverse. Right? For the tangent inverse, you look up the formula, which I will remind you here. The derivative of this. Let me remind you here. Tangent inverse x derivative is equal to 1 over 1 plus x squared. Okay, so remember this. So we're using this here. So now it becomes 1 over 1 plus x squared. But this x squared here is replaced by the inside function x over a. That is just the first step of the chain rule. And the second step of the chain rule is to derive the inside function, which is x over a, right? So this, we get another x over a, 1 over a here. Okay. So now, simplify this. We have 1 over a squared times this 1 plus this kind of x squared, a squared, right? And this a multiplied through the bracket, so we have 1 over a squared plus x squared. Okay, so that is the answer for the first one. Now let's take a look at the second one. Second one is here. So you see that for all of these questions, it has the inverse function, so you must memorize the formula for the derivative of the inverse function from your formula sheet. Otherwise, it's gonna be impossible to do this, because you can't just derive the derivative from definition every single time. It's very time consuming to do that. And in your exam, you can't afford to do that. So make sure that you memorize the derivative of the inverse trig function very well from your formula sheet. So now let's do this. This is dy over dx equal to, so chain rule here, right? The derivative for our sine inverse function is, which I will remind you here. So sine inverse x derivative is equal to 1 over this 1 minus x squared. Okay, so this guy here. And we're using it right now. So it becomes 1 over 1 minus, of course I forgot this square root, 1 minus this x squared. But this x here is now replaced by the inside function x squared plus 1 bracket square. Right? So that is just the first step of the chain rule. We need to multiply this with the derivative of the inside function, which is the derivative of this one. Derivative. So from here, you would either want to use the quotient rule, or you will need to rewrite that expression a little bit so that it makes the derivative easier to compute. So it becomes now, if you don't want to use the quotient rule, you will want to write this as x squared plus 1 minus 1 over this to the derivative. And in the same time, I'm changing this into 1 minus x to the 4 x squared plus 1 square. And the other factor here becomes 1 minus 1 over x squared. The advantage of rewriting this is now you have a constant in the second factor whose derivative is just 0. So you can avoid using the quotient rule, which is complicated. So this becomes this negative of x squared minus plus 1 to the negative 1 derivative, right? So it becomes this negative 1, right? And the negative 1 from the power comes here. Chain rule gives that is to the negative 2 times 2x. And you cross out those negative 2 negative 1s, cancel out. So it becomes like a times 2x over x squared plus 1 square. Right. And you can split this x plus 1 bracket square, write it as x squared plus 1 bracket square, has square root here, times this x squared plus 1 is 2x. So this is just purely algebraic manipulation. It should not be too difficult. And the reason I'm doing that is because I want to multiply these two denominators to just simplify the expression. So if you multiply these two guys, you see that this becomes 1 over, this is x squared plus 1 bracket square minus x, well, it should be x to the 4. Is 2x over x squared plus 1. And this simplifies to 1 over, if you open the bracket, you see that this is 2x squared plus 1 times this is 2x over x squared plus 1. This is the final answer. Should not be too difficult to see. right? It is a little bit complicated, but it's not too difficult. Okay, so that is the final answer for the second question. Okay, so now let's work out the third one. Question C. We should have enough time to do that. Okay, question C here. Is dy over dx. We need to apply the product rule. Right, there are two functions here. The first function is x. Another function is this sine of this some cos inverse x. So it becomes the derivative of the first factor, which is the derivative of x, which is 1, right? Multiply the second factor, plus the first factor multiplied with the derivative of the second factor, which requires the chain rule. So it becomes cos here of this cos inverse x, right? Chain rule, and the next factor is the derivative of the cos inverse, right? The cos inverse, if you look up the formula, that is -1 over square root of 1 minus x squared. So I'm writing this out to just remind you the derivative of this guy is -1 over this one here. Okay, so that is the derivative. Very simple, but speaking of simplifying it as much as possible, it requires us to work with the inverse trig function. So the inverse trig function here, let's work with the first one, right? What is this first one? Can we simplify this? So if we let this thing inside be theta, then we have, by definition, that cos theta is equal to x, right? When cos theta is equal to x, what is sine theta, right? This thing is essentially sine theta. So sine theta, it's plus or minus square root of 1 minus cos squared theta by the trig function identity. And here we need to choose the sign. How can we do that? How can we choose the sign? So keep in mind that this cos inverse, right? This inverse, this thing, is inside the interval 0 from 0 to pi. And we know that when theta is inside this 0 from 0 to pi, the sine function is positive, right? So sine function is positive, which means that we only need the plus sign. There's no minus sign here when theta is in the first or second quadrant. So well, it means that the expression in the first term here simplifies to just 1 minus cos theta, right? 1 minus cos theta. Cos theta here is 1 minus x squared. So this is 1 minus x squared for our first term. And for our second term, this x is here. And we have mentioned that whenever we see this kind of thing, this function cancel with the inside the inverse function, right? Because this thing is in the inside is different from that when this is in the outside. When this is from the outside, we need to do a little bit more work. When this is when the inverse function is in the inside, we can just cross it out as long as this x is inside the domain, right? And because this expression is given, it implies that x is always inside the domain. Otherwise, this function will not make sense. So we cross it out. So it becomes just x here multiplied with negative 1 over this 1 over x squared. And then it finally simplifies to this is minus x squared. And if we combine these fractions, it becomes 1 minus x squared, 1 minus 2x squared as the final answer. Okay, final answer. So that is our question C. Maybe we still have time to work out the last question, question D. And if so, let's do that. Where is question D? I've lost question D. Okay, question D is here. dy over dx. Obviously, we need chain rule. And the first layer is the ln. Right, we know it very well. The derivative of the ln is 1 over that inside function. So it becomes 1 over this sec. That's the derivative of the outside. Then we times the derivative of the inside function. That is the derivative of the cosecant. Cosecant, I'm writing that here. To remind you, is a little bit complicated. This guy derivative is equal to 1 over absolute value. Okay, this is x squared minus 1. It's very complicated. And then we apply it here. So it becomes absolute value of this 3x multiplied with square root of 3x bracket square minus 1. Simplify it a little bit. And this 3x. And this becomes 9x squared minus 1. And that's it. Very simple. As long as you remember this formula, it should not be too difficult. And you can see now for the derivative, it actually not as difficult as the previous question because they are just mostly computation. As long as you remember those formulas very well. But for the second question, you do need to understand how the step works. It's a little bit tricky sometimes. It requires the identity. So a summary for this worksheet. The first question, you need to know the steps, the technique to assume the inverse function to be theta and use the definition to rewrite the expression. And I also emphasize that when the inverse function is in the inside, that is different from when the inverse function is from the outside. When it's in the inside, you can just cancel it out in most of the situations. But when it's from the outside, you need to find that, reduce this thing to a small angle. So that is the unique theta that is in the chosen interval. Okay, so that's it for this worksheet today.